I was going to say, there is no 3.5. It's too late.
All right, guys, so if there's no questions on homework, what I want to do is do the section 4.2, get that out of the way. And then focus on talking about 4.3, the rest of 4.3. So 4.3 talks about the second derivative. Everybody. 4.3 talking about the second derivative, what it means visually, what it means for a graph, right? So we know what the first derivative means for a graph. So I talked really quickly about the idea behind Rolle's theorem last time. This is section 4.2. I'll knock this out real quick. I'm not going to get too deep into the proofs of these things, but these things are used for a lot of proofs of theorems after this point. That's right. So the basic idea of this sort of made sense. So if we have a function f continuous on a, b, differentiable on a, b. So it doesn't have to be differentiable at the endpoints. So this is 1, 2, and if we know that f of a equals f of b. All right. Well, let me let you absorb that. A lot of our theorems start with continuous. Some of them say that it also has to be differentiable. So continuous on AB could look like this. That's continuous. But that would not be differentiable at that point, right? So together these guys, so if it is differentiable, it actually is also continuous. The only reason I say both is because this has to be on the closed interval. This could be on the open interval, right? I like that I made the same symbol twice. And if I happen to know that the endpoints have the same outputs, it's almost kind of silly to think that this couldn't be true. I mean, this is like an obvious thing. Hopefully this is obvious. If these two have the same value, then there is at least one point C somewhere in there where the slope from A to B is the same as the slope at C. So what I can say there, how would I get the slope from A to B? Well, in this case, for Rolle's theorem, what's the slope going to be? It's going to be 0. So the slope from A to B is 0 for Rolle's theorem. The mean value theorem says it could be anything. It just kind of picks this picture up and turns it so that it could be like that.
Could there be like any number of paths?
Yeah, so at least one. There's at least one.
Oh.
Then there exists, so if all this is true, this comes from this, and also if all this is true, then there exists, I like that. And sometimes I might use this symbol for there exists, the backward E. The backwards E means there exists, just in case I do that without thinking, I almost did right there. Then there exists at least one value C, go ahead, A less than C less than B, where f prime of C equals 0. Okay. It took a lot of writing for a very, 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 very crazily simple idea. There's no way you could possibly imagine that, well, obviously if it's a straight line,
There's plenty.
the slope of the whole line, any point on the line would be satisfactory, right? The only way I can make there be one point would be if I did like that. But any way you can imagine connecting A to B. Right? I said this last time very quickly, and I can't really say it to make it any clearer. The minute I'm not going straight, the minute I'm going one direction or another, I'm going to eventually have to turn to come back there, at least once. But as many of you guys pointed out, I could have something oscillatory, and it's got a bunch of places. So if I have something that's more like, then I've got there, that's 0, there, that's 0, that's 0. Because it's continuous and differentiable. It can't escape having somewhere where it kind of slopes so that it's a 0 slope. Just because it's got to come back. The minute it's going away from the straight line, it's got to come back to it. So somewhere in the middle, it's got to have an equal slope to it, a parallel slope to the x-axis. All right, how's that so far? Okay, it's almost too simple to believe that they made a theorem out of it. There it is. And then they said, and here's the one that's a little more interesting than this. Just let me draw the classic picture here so I can do what I want to do. So here's the classic picture that's drawn. So then you have your place where it's a horizontal tangent. So what the mean value theorem, so Rolle's theorem is here. And if I generalize this to f of a, not necessarily equal to f of b. All right, so I take this last thing away. Then I get the mean value theorem. And again, there's a ton of ways to make this work, but if I just pick this picture up and rotate it so that b is up here, the output of b is up there, not equal to f of a. So I got like a, and this is f of a. Let me make it more general. Here's a, here's f of a. Here's b, here's f of b. Right there. Oh. Here is the straight line from A to B. Stop there. So it's really kind of comparing the way to get from A to B either as the crow flies versus any other route you take. You're eventually going to have to be parallel to the as the crow flies path. You're going to have to be. So this would be as the crow flies. We live in San Diego, so there's a giant canyon right there. So I can't do that in my car. So I drive this way. So just take this idea where there would be a horizontal tangent line somewhere because of the setup here and just rotate yourself. And there it is, the same damn thing. Yes, sir?
Does that change all 3 dimensions?
Yeah, there's a 3-dimensional analog to this. That's not part of what we cover here.
But are these still applicable in 3 dimensions?
There's a 3-dimensional analog to this theorem. Yes, but you have to be a lot more careful because there's a lot more directions you can go in. So then you have to be very specific. Then you get things that are called directional derivatives. Right? Because in more here I can only move along the x-axis and talk about what my function's doing. If I have 3 dimensions, I can move along the xy plane and my function's doing shit above me. So it depends on, am I looking that way or am I looking that way? Because it could be, think about on a mountain. Can you imagine on a mountain? If you look this way, it's like this. If you look that way, it's like this. So the derivative this way is very different from the derivative that way. You guys kind of follow? Mm-hmm. Now that went beyond what I wanted to say here. That's a little taste of Calc 3. Right? So let's bring it back to 1. Oh, that was close. Shit. You guys ignore it. So somewhere in here, so the same idea. Somewhere in here there must be a C such that the slope at C is parallel to the as the crow flies path. That's the idea. And of course, it almost is too silly. If we accept this is true, then just rotating it, it's the same place. Right?
Yeah.
So if this is true, then this has to be true. Okay. Now there's a lot of little technical details you take care of in the proof of it, but the idea of it's so simple, you're like, well, this must be true. Right? But when you prove something, you have to be really technical. This is as deep as I want to get into the explanation of why this is true. But it just intuitively makes sense. Right? Now, so what the hell are the problems going to look like? That's a good question. So let's do a straight up problem.
Straight up.
Straight up. Let's see. Blah, blah, blah. Let's do this. Here we go. This is 4-2.
It's 4-2.
4-2.
I know.
What happened?
I was asking if it was 4-2, but you said it was 4-2, so I get it.
It's not. It's 4-2 everybody. Let's see. So if I say okay, this on this, are the requirements met? What are the requirements for mean value? There's 2 of them. It's got to be continuous? Yeah, so radicals are continuous everywhere. This would be discontinuous Yeah, it doesn't exist in the negative domains. But this is fine. My interval is fine. And it's got to be differentiable, so it's got to be continuous on 0, 4. Get out of there. And it's got to be differentiable. Now, where on this is it not differentiable? Actually, there's a point where it's not differentiable.
0.
At 0, but thankfully it just requires that it's differentiable on the open interval. So it doesn't have to be differentiable right at 0. Right at 0, this actually has an infinite slope. But I'm not going to get there. Nah.
What does that even mean?
All that means, now real quick, good question.
You try
so
to get close.
As the square root comes in, it starts to dive. So right here, it's actually
Still diving.
has an infinite slope right there. That just means it's like if I'm coming in there and going, at some point you're just going to start to fall straight down. That's an infinite slope. That is complete rise, in this case fall, with no run.
Alright.
That's all it means. So it's like, shit. And it hits the ground right as it's about to, shit. Okay, stop.
So
I got this whole scene in my head now. It's really freaking me out.
If you had a straight up and down graph, that would be infinite slope.
Exactly. In fact, if you looked at stuff like, what do you got, Jeff? X to the 1/3. This is even more interesting because it's got both sides.
Coming at it.
Right here, the tangent line would be infinite. Infinite slope for the tangent line. Right at the center. And of course, if you took a derivative, then would this be 1 over 3 cube root of x squared root?
Yeah.
So at 0, it would be an infinite slope. There you go. All right, I like it. So this does not have that problem because I only have to be differentiable on the open interval. I like it. Cool. So I want to find C where f prime of C, the slope of the tangent line at C, I want it to equal the slope of the function between these two. So how do I find the function between, how do I find the slope of the function between A, f of A, and B, f of B? 3 f of B minus f of A, y2 minus y1 over x2 minus x1. Good old stuff. For some reason, the book likes to multiply this thing up and make it look like some linear approximation crap. Don't do that. Just keep this like this. It doesn't really help to bring that bottom up. Let me stop here for a second because this is the nuts and bolts right here. When they say find C so that you know you got to find this. If it's Rolle's theorem, if the function here is the same as the function there, then the slope is going to be 0. But Rolle's theorem is just a specific case of mean value theorem. I hope you guys understand that. It's just a specific case where this is 0. It's flat if you go straight across. Right. Yes, sir.
What came first, MUT or Rolle's?
Rolle's came first.
Okay.
And then we actually use Rolle's to prove that mean value theorem works. But the mean value theorem is actually kind of Rolle's more generally, right? So, but Rolle's did come first because you use it in the proof of the MVT. All right. So how does this work? Well, in order to do this, what do I have to do first? Or I can do a couple things first, but what do I have to do?
Find points, f of b, find f of a.
All right, cool. So we'll do this side first then. I like it. So I'm talking about square root of x on 0, 4. So what is f of 4 minus f of 0? There's my a, my b.
2 over 4.
Yeah, f of 4 is 2. F of 0 is 0. So that side is 1/2. How's that? So the whole idea of mean value theorem is to find a point, an input, where the slope at that point is the same as the secant line between the endpoints of the interval. And again, if you remember, it just makes sense. If it's not a straight line to begin with, it's got to eventually curve back. There's got to be at least one place. You might find multiple places. So that's that side. How do I find this side?
Take a derivative.
No way. All right. So this is, you can have Jeff, that is the right-hand side. And now let's look at the left-hand side. I've got to find f prime. What's f prime?
1/2.
We'll have x and we'll have.
So 1 over 2 rad x. Is that cool? All right. So just to be all official, I want f prime of c to equal the slope. So I want 1 over 2 rad c, plug a c into f prime. It's equal 1/2. Well, that you should be able to solve that by sight. Hopefully. What's 1 over 2 times something is 1 over 2. So that something has to be
1 over rad c equals 1.
Sure, you could solve it. Okay. But this has to be 1. Of course it has to be 1 to make 2 stay 2. So c is 1. Why not -1? Because then it wouldn't, shouldn't come out of your work anyway. So c must be 1. All right, maybe. Now let's do this. Let's actually do the rest of this. Let me bring this guy to life here. So let's graph. You guys help me out. You guys figure out. So what point am I at? What point does this represent? The point what? Yeah, square root of 1 is 1. That's right. Take a second. While this guy's warming up, figure out the equation of the tangent line. I've already done all the work for you. There's the slope. There's the point. What's the equation of the tangent line?
Minus 1. So it's 1/2 x minus 1.5.
Whoa.
What?
Yes.
X squared.
Yeah. Plus minus 1. Yeah.
All right, let's try this. All right. It's all nervous. All right, so then you get, what do you get for that?
1/2 x plus 1.
Cool, makes sense. So then at, what's up? You guys all right? That's what you should have gotten. That makes sense. So if I put in there square root of x, so there's my function, and I put in there 1/2 x plus 1/2. Let's zoom 6. Alright, now let's zoom in. Let's make the window -1 up to 5, so I can see my whole interval. And we'll make this -1 up to, what you got, Jeff? 4. Alright, so there's my square root function. Here comes this dude there. And actually, let me graph one more thing that we should graph here. What's the equation from this to this? So this, what point is this? I'll do this one. What point is this? 4, 2. So what's this equation of this line? It shouldn't be too big. Y equals 1/2 x. Cool. So already right there, we're already done. I mean, what's the slope of this line? 1/2. And what's the slope of the tangent line? All right, so they're parallel. So it's almost silly for me to do what I was about to do. If I graph it, it's obviously going to be parallel, right? Do you guys get the idea? So there has to be a point somewhere in the middle. So as I go around the bend here, my derivative is doing this thing. As I go around the bend, so somewhere in the middle, it must be parallel to that as the crow flies path. I like it. All right, that's enough of that. Yes?
Is this just average rate of change?
Yeah, this is just y2 minus y1 over x2 and x1, which we used as a secant line a million years ago. All right, or maybe a few months. Yes?
So what is this used to help with graphing, or what is it?
Mean value theorem is insane. It's used in so many proofs dealing with slopes in any way. The mean value theorem comes in a lot of places. So in section 4.3, there are several proofs of things that require the mean value theorem to work. Cool. So what immediate use does this have? It's hard to really say, but it's used as a primary thing to get us through theorems, to prove theorems are true. If we can't prove theorems are true, then we can't use them. I like it. I like it. Cool. Okay. One more problem, just to show you how it can get a little bit freakier, of course. That shouldn't be a surprise. So that's your classic nuts and bolts problem here. Find the point C that the mean value theorem says is supposed to exist. And there might be multiple answers. So what about something a little more interesting?
Ready for the interest.
Let's see. What about... Ooh. I can't remember what I signed, but... Yeah, this sounds very strange. This is number 23 in section 4.2. If f of 1 is 10, and f prime of x is greater equal to 2, for 1 to 4, oh, I can love it already. How small can f of 4 be? So why would mean value theorem possibly work? What has to happen in order for mean value theorem to be guaranteed to work? What must happen? Continuous and differential. This tells me what?
Your slope is 2.
But be less specific. Related to what the mean value theorem needs to be true. It's differentiable on this interval. Cool? So the mean value theorem is like, okay, cool. So I will work on that interval. I'm guaranteed to work on that interval. I like it. So they didn't say it. They just gave us symbols, but we have to know what the symbols mean. So I can use the idea of the mean value theorem here.
So if it was just 1 less than x less than 4, it wouldn't be continuous because it's less than or equal to?
Well, no. If it was less than, we'd be fine. They just say great equal to because they start at 1. They talk about 4, so they want us to be on the closed interval. All the theorem requires is that it's differentiable on the open. But if it's differentiable on the closed interval, that's just even better. Does that make sense? So it's like, oh, it's on the closed. Not the, oh, no, it's even better. It's even stronger. Does that make sense?
Okay.
So theorem's like, whoa, dude, I didn't need that much shit. But sure, I'll look for that too. Alright, so this is very, very strange when you first read through it. But then when you see the idea, any problem like this is going to be pretty simple. So let's see if anybody can see the idea. So if f of 1 is 10, and the slope is, now you can be specific, the slope is at least 2 from 1 to 4. So the slope, of course, tells me how much I'm going to increase as I move over. So I'm going to go from 1, and they're asking me about 4. So really this question really is asking, what's the least steps I could take from 1 to 4? The least amount that I can go up from 1 to 4. Right? So this is 2 for every 1. That's what's the smallest the slope can be is really what the question becomes. And it tells you the smallest the slope can be is.
Can it not be negative? Like, can the slope be negative?
What's it say? The slope must be greater equal to 2. So the least the slope could be, which is going to give me the smallest f4. So let me see if you guys kind of get this. This is almost big enough. But if I make the slope big, then my f of 4 is going to be big. If I make the slope smaller, then my output's going to be small. And that is asking me what's the smallest it could be. Yes, ma'am?
How do you know that the slope is 2?
It told me it's at least 2. You with me? Now I'm investigating how does that relate to this.
Oh, okay.
If I want to make the output big at 4, then I want to rise very fast, don't I? I want to rise quickly. Because then if I'm pointing this way, at 4, it's going to be a huge output. Holy shit. But the question says I want to make it small. So I want to make my slope the smallest I'm allowed to. And what's the smallest I'm allowed to make the slope? 2.
So it's
60.
Yeah, so if it's, so I'm taking how many steps am I taking? 3. So if it's 2 to 1, it's 6 to 3, so it's going to rise 6, so it's going to go to 16. Yeah. And it's not the only way you can do it, but to me that's the quickest way. Almost, hopefully some of you guys are at least on board with what's happening. Almost is too easy to even really, maybe for some of you, understand what just happened. It's like, all I did was algebra level shit, really. Right? Apply the slope to get from 1 to 4. You just move up and over, up and over, up and over 3 times. Right? That's all we did. The trick is, I actually did use... What's up?
Wait, why 3 times again?
Because where did I start?
1.
And where do I end up?
Oh.
So I'm just taking 3 steps. Cool. So slope is all about this much change in the y for this much change in the x. So if I want to change the x by 3, I got to change the y by, in this case, 6. I like it. So there are several problems in the homework that are very similar to this. And now I'm hoping by showing this example, you kind of know how to think about it. Right? So they could have a similar one that would say, make it the largest you can, and then you just make the slope the largest you're allowed to, and then you do the same thing. I like it. They're not all going to be exactly like that, but at least they use the same idea, the same thought process. Okay. Let me see if there's anything else freaky. Oh, if they ask you a question about that, for example, on, I don't know. Yeah, this. Okay. Can mean value theorem help you? If they ask you questions about the slope on this, can mean value theorem help you?
No,
Why not?
because it's not differentiable. It's not differentiable.
Yeah, it's not differentiable. Even more fun. Why? Why is it not differentiable? Where?
Because you have the square root down the bottom. Or no, there you go. But you can
Yeah,
use the
well,
0,
it makes
because it's not differentiable.
Yeah, where does this thing become 0 on the bottom?
3.
So it's not even continuous
Yeah.
on the interval at hand. So the mean value theorem says, shit, anything can happen. I don't know. So if the conditions aren't met, that doesn't mean that there doesn't exist a C. It just means the mean value theorem can't guarantee it. It's like, I don't know what's going to happen. Anything can happen. Shit, this function's going all over this.
So do you not do anything on that problem?
So there's a problem in homework that says, apply the mean value theorem anyway. Why is it okay that you couldn't find C? You can't find a C to do what they want you to do. Why is that okay? It doesn't even meet the requirements. So it's kind of a funny question to me. I wouldn't even have done the damn problem, but they forced me to. And I'm like, well, I didn't find C because the stupid thing wouldn't work. It's fine. The mean value theorem doesn't guarantee it to be true. So if you don't meet the requirements of a theorem, its conclusion is not guaranteed. Yes?
So, for
You
the
just apply
explanation,
this,
would
yeah.
you just say, because it doesn't qualify the mean value theorem, which states like it has to be differentiable?
Yeah, exactly. So you can say either one, because it actually is not differentiable either at 3, right? I can take this guy's derivative, but when I try to plug a 3 in, of course, I'm going to get undefined slope. But it's not even continuous, which is a little bit less strict than differentiable. So it's not even continuous, a poor little thing.
Okay.
I like it. Okay. That pretty much covers all the kinds of things you'll see. You'll see simple, straight up, find the C, and everything's beautiful. You'll see this kind of stuff. Why is it okay that it doesn't work? Because the damn interval doesn't work, right? It has problems somewhere in the interval. And then you'll see ones like this. Okay. Maybe. So let the idea of the theorem be as simple as it is. It actually is a remarkably simple idea for a theorem. The applications of it get a little freaky sometimes. Okay, so what I want to do is to go back and finish up that handout from yesterday. But then I also want to bring in the second derivative eventually. They may not get the handout from yesterday.
I don't know.
Maybe. Let's see. I should have enough. You got it?
Yeah, it's red.
Oh. Oh. There it is. Anybody else need that? Come on, which one are you? That is freaking me out. See if it can find itself. There we go. All right, so last time we did that first part of it. And the whole idea we were focusing on here is kind of the first steps in 4.3 and 4.5. So what I'm actually going to do today is I'm going to basically do 4.3 and 4.5. And then we'll come back and do 4.4 after that. Just because, to be honest, 4.3 and 4.5 are the same damn thing. It's really funny. 4.3 focuses on specifically calculus-related stuff, and then 4.5 says, oh yeah, the calc stuff, let's put it together with the pre-calc stuff you're supposed to already know and graph more things. So it's really the same exact thing. So that's why I'm going to do it. Even if you disagree, I'm still going to do it. Alright, so we did that last time. So let's see what's going on with this one. Alright. So I don't know if anybody had a chance to do this yet. I don't think we got that much time last time. How do I take this guy's derivative? Kick ass. Yeah, so the derivative of x is 1, so e to negative 2x squared. Yeah, good. So it's going to be x times the derivative of this, which is e to this, times the derivative of the inside, which is going to be negative 4x. So negative 4x times the x that's already there, times the e, which is its own derivative. Now notice you never change the inside of e, because the derivative of e to something is e to that same thing. You never change the exponent itself. Is that cool? Because it's not a power rule. It's not. It's its own rule. How do I simplify that so I can set it to 0 and stuff? Yeah, take this thing out of the way.
1 minus 4 squared.
Cool, which is... This is a thank God problem is what I call it.
2x plus...
1
The derivative is already
minus
2x.
2x.
And then
1 plus 2x.
1 plus 2x.
Cool.
But it's
Yeah, well, so we took it one step further. So we showed that it is equal to this, and then we can factor that piece a little bit further. So again, just to remind you guys, on the test I'll do exactly this. I'll say show the derivative is this. So in case you have any trouble getting the derivative, you can at least still finish out the problem. So how do I find the critical numbers? So let me write here the better form of this. Critical numbers, I can just see them now, right?
Plus or minus 1/2.
Yeah, good. Plus or minus 1/2.
And then,
Does this guy give anything?
No.
He does not give me anything, because e to a power can never be
0.
0. I like it. It can just get small, small, smaller, big, big, big. It can't become 0. Just trying to be a plus. Okay, cool. I like it. All right, so this has got to become kind of like a normal. In fact, this is why I try to make a little bit of a point about factoring early on, because this is going to be a big part of what we do, and a lot of what we do. Calculus word problems are in our future. I just wanted to say that to freak you out. But it's true. And they're nowhere near as evil as some of the word problems you've done in your past. But the only way they can be evil is if you have trouble with the calculus itself. It's just derivatives. Alright. So how do I do this? Make a sign diagram? What the hell does that mean?
a straight line, you get 1/2.
Yeah, so put my critical numbers down there. I get 1/2, 1/2. That's where the derivative is 0. It wasn't undefined anywhere, obviously, right? Just don't forget you got to check both of those. Where's the derivative 0? Where's it undefined?
So it's positive in the middle.
Good. So when you plug a 0 in,
Just positive.
you get... I'm going to use this guy. You get 1 times positive. This guy is going to be always positive. So it's all about this dude here, right? So when I plug a 0 and I get positive, the multiplicities of these are 1. So it's going to change sign everywhere. And if you don't like that shortcut, just plug in a 1. You'll get positive times negative times positive is negative. And the same thing, if you plug in a negative 1, you get a very similar thing. I like it. So it's really good to identify the parts of the derivative function you're dealing with that won't change sign, that are always positive or whatever. So you only have to worry about the other parts of it. And you don't even care what the number is, you just care about the sign. So can you take a second, don't say anything, just below this try to give me a rough sketch of what it might look like. You could very easily be wrong, but it's just a rough sketch. Yes, ma'am.
Are we graphing the function or the derivative?
We're graphing the function. Yes. So down here, what's this mean?
Increasing.
So it's going down, it's flat, and then it's going up, and then it's flat, and then it's going down. I like it. So the information we're missing, the reason I said what I said is because I took some liberties with something there. It could have looked like this. Down, and then flat, and then up. See, so I have a different kind of, so this is this way and this is this way. They're both going down, they're just going down in different ways. Right? So we're going to talk about the differences there. And that deals with the second derivative. Some of you guys know where I'm going. Concavity. Kick-ass. So intervals where it's increasing, where's that? Negative 1/2 to 1/2. Decreasing?
Negative infinity.
Yeah, negative infinity, negative 1/2. 1/2 to infinity. I like it. Kick-ass. So increasing in the middle, decreasing on the outsides. Max is a min. Is there a min, max? How many things are there?
Yeah, there's a
Minimum.
So there's a minimum where? Good, negative 1/2. Something. It's not going to be pretty when you plug that in there, right? I doubt that e to the negative 3 times 1/2 squared is going to come out nice. Yes, ma'am.
So for local maxes and min, you actually find the point, but for absolute maxes, you don't actually.
Well, because for absolute, this is going to be used, the next thing we're going to do with this information, we're going to graph it. So I want to know the point, and I'm going to write the word minimum next to it. So when I graph it, I know as I come to it, I'm supposed to be doing this there. Do you see what I'm saying? So if I label what the point represents, graphing is going to be relatively easy. You just say, it's supposed to be minimum, I better not go below there. Right? So that's the next thing. That's why we want to find the point. Anybody do that for me? Or are you guys just sitting around? Is everybody waiting for everybody else? Somebody's going to do it, and nobody did it. I like it. Is that sort of like voting? I don't know. That's fine. They'll vote for somebody. What the hell just happened? So I don't know. I just want you guys to do that. Make sure you guys can use the calculator. Where are you plugging it in, by the way? Good. I want to know where the function is, not what the function is doing. So I've got to plug it back into the original.
Yeah, negative 0.3.
Sounds about right. Let's see. Oh yeah. All right. So this is negative 0.3, and this will be positive 0.3, roughly 30326. You guys getting that?
Yeah.
It's right if you're not, because Christian and I can both be wrong. You never know. All right. So then I can plot those and do things. So what I want to do now, we did this one last time. We just did this one here. So the idea of finding critical numbers and then using those critical numbers to identify maxes and mins. How do you feel about that process? The more you understand that process, the more you're going to understand what we're going to do with the second derivative, because it's the same damn thing. They just have different meanings because it's the second derivative. We've got to figure out what the meaning of it is. So this is related to when people say in the news, they say something like, the rate of decrease of the economy is decreasing. And you're like, okay, wait a minute. You figure out, you plot what you're saying. So the rate of decrease in the economy is decreasing. So what? It's still doing what? If I say that, what's the economy still doing?
It's still going down.
Still going down.
But it's
Shit.
at a decreasing rate.
Yes, so the rate at which it's decreasing. So that would mean it's going down, but it's not going down as bad. And what we hope is going to happen is that,
A local
and of course
man.
what sometimes happens is it says, Are you guys kind of with me? If I said the rate at which the economy is decreasing is getting bigger, let's try to say this again. The English gets really interesting here. The rate at which the economy is decreasing is itself increasing. That means it's going down
Faster.
faster. So how would you draw that if I said it's decreasing but it's going down even faster? Yeah, it's going to be like, it's got a negative slope, but the slope is getting more and more negative. This has got a negative slope, but it's getting less and less negative. So that, if you think about it, what should the second derivative represent? Put some stuff together for you.
It represents the slope of the slope.
Yes, so let's say it a different way, because that's a little freaky, right? So, f prime represents the rate of change in the outputs, right? Per x. As you change x, what's the rate of change of the outputs? So what should f double prime, and again, whenever you have a function, I don't care if it's a derivative of something or what it is, when you take its derivative, you found the rate of change of it. So this would be the rate of change of f prime per x, right? Because they're moving along the x-axis. Right? So this is the rate of change of the slope. So this is acceleration, isn't it? Because acceleration is the
Double prime of
second derivative of position. And acceleration's units. What are acceleration's units?
Meters squared per second? No, meters
Meters
cubed.
per second squared.
Yeah, meters per second squared. So what that really is, it's this. It's the rate of change of the slope of position per second. So what acceleration does is, if it's positive, it keeps adding velocity on as you let time pass. That makes more sense. And of course, math people would go, I don't want to write SEC twice. Let me make it make less sense, but save myself some time. And then students are like, what the hell is a square second? And I don't blame them. I'm like, I don't know what the hell a square second is either, but it's just a way of collecting shit. But this actually makes more sense when you think about it like this. Yeah.
Okay, so you're saying for the first derivative, we're looking at like where maxes and mins are. So the second one is where like it's increasing and decreasing.
Yes, so let's get more specific. Let's tie together what we're doing over there about the economy and stuff.
Okay.
And let's really get a little more specific about how to interpret this. You ready? Even if you're not, you're going to do it. So if I said that this was positive, all right, what should be happening? So let's say, let me give you a starting point. So
The acceleration is increasing, which means
so let me give us a little bit of a starting point. How do I want to do this?
that's a positive velocity. So, what are you asking?
So if this is, so let me give you this. Let me do it this way. Let me give you a picture.
The derivative is increasing.
All right, this is rough. ABC might actually not have anything to do with this answer. But let me just see if you guys get this. So where is this true roughly on this picture?
From B to C.
So I want the rate of change of the, how do I say this? The rate of change of the slope to be positive. So if it's negative, I want it to be getting less negative. If it's positive, I want it to be getting more positive. So right here, what's the slope? Is it positive or negative? Positive. But what's happening to the poor dude?
It's getting less positive.
Getting less positive. Shit. So where's the slope getting more positive? Here it's negative, but what's happening to it?
Less negative.
So here, if I draw some tangent lines for us, that slope is negative, but it's getting less negative, so it's getting more positive. You guys understand that? So around here, around this turn here, it looks like the tangent lines are getting more positive. And here, they're positive now, and they're getting more positive. So it's adding on more positive. So that is where this is true, in this area. So now watch. Remember that little point we talked about before? And I couldn't really talk all the way about it, but somebody said it was an inflection point, and now we're going to talk about it. So right in here somewhere, there's a point where it stops getting more negative, and there's the most negative point, and then it gets less negative.
So that's the zero.
That's where f double prime
Is zero.
is zero, exactly. I like it.
Is that where we get the two lines with the first derivative, where you show the plus and negative, and then the second, you got the plus and
Yes,
negative?
exactly. So you do it first derivative test, and then you do the second derivative kind of test to see where the inflection points
And
are.
then
So
when they're like opposite, that's when they're one.
oh, no. Now, when that would be more of a question from the section with the particles moving.
Oh.
So when is it speeding up? Then the acceleration has to be the same sign as the velocity itself.
Oh.
So if my acceleration is the same sign as my velocity, the acceleration is adding more velocity in that direction. If my velocity is positive and my acceleration is negative, then I'm slowing down. I'm starting to go that way more, right? So that's that level. It's not really talking about concavity then, it's just talking about how they affect each other. We're talking about how does this relate to what the picture looks like. That's a different, not totally different, but different idea.
So is this a picture of f of x, f prime, and f double?
This is f prime. I mean, this is f. This is f.
Okay.
Yes, cool. I like it. Good question. I forgot to say that. That is the good question music.
Sounds like a great day.
Now, every time somebody asks a question, I need that to play. Okay. So, obviously, I'm hoping that, and here's the interesting thing. What would you say is true? So, when this is true, what shape does it take? Okay, let's go right to it. Concave up, and very often what we simplify that to is we just call it cup up. It can hold water, or H2O, because I can't say the word water correctly. All right, so that's cup up.
The red part is the cup up.
And you gotta love the fact that cup up happens when the freaking thing is positive. Oh, thank God, math, right? And math is like, dude, what me? It's just the way the reality is. There you go, thank God, reality. So down here, what am I gonna call that? Remarkably enough.
Concave down.
No way. So this is concave down.
Cut down.
And I don't know if you guys know the difference between convex and concave, but if you do, you understand the words we're using a little bit more. So this is cup down, won't hold water, right? This is if you're very drunk and you're worried about who stole your drink. You know, you just held the cup upside down. So it's a very simple case. Done. I'm not speaking from experience. So, I think somebody else just said this, and I said this earlier. What's going to determine when the change is concavity? Inflection point. How am I going to find the inflection point?
Test it like the second.
Find it where it's zero. So R is, here's the key. Now you know the answer to this. Everywhere that this is true isn't necessarily an inflection point. No, just like critical points. Critical points of the first derivative are where the first derivative is zero. Are they all maxes and mins? No, it could be a little bullshit, right? So the same thing could happen with the second derivative. They are critical points. I call them critical points of the second derivative. Right? Sounds sort of like close encounters of the third kind, but let's try a problem out. And actually, let's just do the one I have right here. We'll do this one together.
Good.
Already there.
What's up?
Drew over the line. Already there.
Yeah, I know.
What's the habit?
Making it more
lining.
or line.
Most line.
The rate of increase
There's
in the
already a
thickness of the
line.
line.
That's strawberry though.
What section is this?
Okay.
This is 4.3/4.5. 4.3 introduces the idea of concavity. and what it means graphically. 4.5 just says we're also going to find asymptotes, stuff like that. It just adds in pre-calc stuff.
Show that I'm fine with x equals 15x squared.
You take a minute and just verify, do part A.
Do the derivative.
And part B, you might as well do both.
X squared x. And the critical numbers for f prime x can be 0. Yep. Make a sign diagram. So here, 0.
Well, this one definitely is not as evil as the one we did the other day, right? This one should be a lot better. So you should be done with part A by now, right? And to give you a little clue, if I'm going to go do part D, I'm not going to start here. Screw that shit. That's a 3-term product rule. No. So the very first thing when you did F prime, what'd you actually get? Before you did anything else, what'd you get when you did F prime?
15.
Yeah, right? And then you factored it. But if I have to do another derivative, I'm not going to start here. I'm going to start freaking here. Shit. You don't. They're the same thing. Just one is factored, one isn't. So if I ask you for further and further derivatives, use the form of the function that's the easiest to take the next derivative of, because they're all the same. And then this is quick. Cole, can you shut that light on? It gets the yeah. Cool. All right. All right, guys, you should be done with part D. I'm hoping. So let's come back up here. Are you guys working on part B? What are your critical numbers there?
0,
0, 1, and -1. I like it. Cool, because there's nowhere where it's undefined. Then my little sign diagram.